Welcome back to linear algebra. In this video, I want to talk about the inverse of a matrix. The idea of an inverse is something that gets thrown around a decent bit in the discussion of mathematics, and it's one of those ideas that I very often see students look at, kind of sort of remember, and then not really. Let me get my head out of the way, and let's go through a quick review of places you've seen the inverse in the past. When you first started learning arithmetic, you studied the additive inverse and the multiplicative inverse of real numbers, although it was probably several years after you first were introduced to the concepts that you gave them a name. For some number a, the additive inverse is another number, the opposite of a, which is designed in such a way that if you add a and opposite of a, you get the additive identity 0. The multiplicative inverse is the reciprocal. If you have some fraction, a over b, and you multiply it by some other fraction, b over a, you get 1. Then as you continued onward into algebra and towards calculus, you come across the idea of the inverse function. And an inverse function is defined under composition. F of the inverse of f evaluated at x is x, and f inverse evaluated at f of x is equal to x. That last one is really the idea that we're looking at when it comes to the inverse of a matrix. Because as we're pushing ahead, our goal, the place we're going to end up, is showing that a matrix is a nice way of defining a function which acts on vectors. But for right now, the vocabulary is going to look closer to the multiplicative inverse. So if I have an inverse matrix, I'm looking for some matrix that I can multiply A times some other matrix I'll call A prime for right now. All right, quick aside there. For those of you, most students come into this course directly out of calculus. And in calculus, you learn to use this notation of prime to mean derivative. Prime itself doesn't mean derivative. D over dx means derivative. Prime means something different. So we have a matrix A, and we have some matrix that is different from A but related to A called A prime. In this case, it's going to be related by the matrix inverse rule. In calculus, you have some function f and some other function related to f, which we call f prime. And the relationship that we expect there is the relationship of the derivative. But prime just means something different. So it's not A, but it's related to A. It's something different. We call it A prime. All right, so we need A times A prime to be the same thing as A prime times A, and very specifically for that to be the identity matrix I. One of the properties of matrix multiplication, the dimensions of the result are going to change based on the dimensions of the matrices you multiply together. The only way to get the same identity matrix out of multiplying A times A prime as you get from multiplying A prime times A, is for A to be an n by n square matrix, and A prime is another n by n square matrix. Right? That's the only way we can assure this first step of the equality. If you continue onward in your study of mathematics, you might run across a generalization of the idea of a matrix inverse, which is sometimes called the one-sided inverse, where it will work in one direction and not necessarily the other. And we can define that for a matrix of an arbitrary dimension. It doesn't have to be square, but that's not something we're going to deal with in this course. I'm going to stick with square matrix n by n, the traditional definition of the inverse matrix. So as a theorem, let's let A be any square matrix. If matrix A has an inverse, then that inverse is unique. Notice first thing here, I am not claiming that every matrix has an inverse. And in fact, we'll see a little bit later that not every matrix has an inverse. I am claiming that if a matrix has an inverse, then the inverse must be unique. And I love this theorem because it lets me use one of the most powerful tools in mathematics. That tool is called a proof by contradiction. And this is the classic setup, the classic place where proof by contradiction might show up. When we are talking about something that we say exists, and when it exists, it is unique, this structure of proof is really effective. I'm going to start by assuming otherwise. That is to say, let's take two matrices. I'll call one A prime, and I'll call the other A double prime. And I want to assume that these are both the inverse of matrix A. And my goal is to try to prove that these two matrices must be equal to each other. Well, by assuming that these are both the inverse, then I have a really nice fact, right? I have the definition of the inverse of a matrix to work with. A times A prime is equal to I. A prime times A is equal to I. A times A double prime is equal to I. And A double prime times A is equal to I. All right, those four facts are what I have to work with. And what I want to do is just start with one of these. I'm going to use this one. I could use any of them, but this is the one I want to use. A prime times A is equal to I. Now, the definition of the identity matrix, we've proved previously that if you take the identity matrix I and multiply it times any matrix, for example, A double prime, you get back the matrix you multiplied. So I times A double prime is equal to A double prime. By substitution, I know that A prime times A is I. So A prime times A double prime is equal to A double prime. And I know that matrix multiplication has an associative property. So I can rewrite this moving the parentheses. Instead of grouping A prime times A, I can leave A prime out in the cold and group A times A double prime together. And of course, A times A double prime, I just scrolled it off the screen, but that's equal to the identity matrix. So we have here A prime times I is equal to A double prime. And of course, any matrix multiplied times I is that original matrix once more time. So once again, using properties of I, it must be the case that A prime is equal to A double prime. Right? I love that construction of a proof. Technically speaking, anyone who is studying methods of proof, discrete math, something like that, this is not a proof by contradiction. I didn't actually use contradiction here because I never made the assumption that A prime and A double prime were two not equal things. I just said, let's assume that they are both inverses of the original matrix A. But I tend to think of it as proof by contradiction. It follows the same kind of structure as a proof by contradiction, and that's where the value here comes in. I started off by saying, let's just assume that there are two of these. I used the definition of the thing I'm looking at, the inverse of a matrix in this case. I got a little bit creative with that definition, and I arrived at these two things have to be equal to each other. Proving that something is unique almost always follows this kind of a procedure, and it works really nicely. All right. Now that I know that the inverse of a matrix is unique, I can give it a unique name. A raised to the negative first power as the inverse of a matrix actually works really nicely with the idea of powers of a matrix in general. Right? If you take A inverse and you multiply it times A, you get the identity matrix. If you take the identity matrix and multiply it times matrix A, you get matrix A. If you multiply again, you get A squared and A cubed and A to the fourth. So in a sense, the inverse of a matrix falls nicely into the properties of exponents. And so we can use this exponential notation as a nice way of thinking about it. We use the same sort of notation for functions, and again, that's something that's going to come up in the not too distant future. Matrices are functions acting on vectors, and that's going to be the heart of what we do going forward. But for right now, let's focus on the matrices on their own. Now that we know that the inverse of a matrix is unique, we have a really nice way of finding a way to get an inverse matrix. It turns out we can calculate an inverse matrix by using Gauss-Jordan elimination all over again. And this is one where things can be a little bit interesting. I want to mention with this that if you're following along in the textbook, there is a really nice constructed proof of this process. Starting with nothing else, the textbook derives a justification of using Gauss-Jordan elimination. I want to approach this from completely the opposite direction. I'm going to start by showing you that we can use Gauss-Jordan elimination to find a matrix, and then convince you that that matrix is the inverse. And since the inverse is unique, this is a process that must actually work. Right? It saves us a whole bunch of time and a whole bunch of getting lost in the technical weeds of proof. And let's focus on getting some calculations and getting the hang of doing these things instead. All right, so let's just dive into an example. Matrix A here, 1, 2, 3, 2, 5, 3, 1, 0, 8. Right. And I said that I could find the inverse of this matrix by employing Gauss-Jordan elimination, which means that I want to start off by writing out an augmented matrix. Well, the left hand of that matrix is going to be the matrix I care about. So no surprises there. And then on the right-hand side, well, we don't have an equation that we're working on right now. We have kind of something else going on. The argument is a little bit hand-wavy. It's very much backwards, as I've mentioned. But the goal of inverse matrices is to figure out things that get you towards the identity matrix. And so the other side of this augmented matrix is going to be the 3 by 3 identity matrix. And our goal is to work through elementary row operations step by step, the same way we used for solving systems of equations, in order to get the left-hand side of this augmented matrix to be in reduced row echelon form, as close to the identity matrix as we can get. If we can get to the identity matrix, then we will have found the inverse. All right, in this particular case, we've already got a 1 first row, first column. That makes life nice. So continuing onward, we'll take the second row. We want that first entry to be a 0. It's currently a 2, so I guess we'll subtract twice the first row. And we'll take the third row and subtract the first row for the same thing. That will give me the first column, 1, 0, 0, and everything is going to be able to move on from there. All right, the first row hasn't changed yet. Although it will later. The second row, 2 minus 1 is 0. I'm sorry, 2 minus 2 times 1 is 0. 5 minus 2 times 2 is 1. 3 minus 2 times 3 is negative 3. 0 minus 2 times 1 is negative 2. 1 minus 0 is 1, 0 minus 0 is 0. The third row minus first row. 1 minus 1 is 0. 0 minus 2 is negative 2. 8 minus 3 is 5. 0 minus 1 is negative 1. 0 minus 0 is 0. 1 minus 0 is 1. So I've got first row, first column. I've got the entire first column looking great. A 1 in the first row, zeros everywhere else. In the second row, in the second column, I have a 1, which is just what I wanted. I want to use that 1 to get zeros everywhere else in the second column. So, row 1 minus 2 row 2 looks like it'll take care of that. And row 3 plus 2 row 2 will take care of down below. All right, so 1 minus 0 is 1. 2 minus 2 times 1 is 0. That was our goal. 3 minus 2 times negative 3. 2 times negative 3 is negative 6, and 3 minus negative 6 is positive 9. 1 minus 2 times negative 2 is 5. 0 minus 2 times 1 is negative 2, and 0 minus 0 is 0. The second row stays exactly the same. The third row, I am adding twice the second row. So 0 plus 0 is 0. Negative 2 plus 2 times 1 is 0. 5 plus 2 times negative 3. 2 times negative 3 is negative 6. 5 plus negative 6 is negative 1. Negative 1 plus 2 times negative 2 is going to be negative 5. 0 plus 2 times 1 is 2, and 1 plus 0 is 1. All right, with that, the first column is looking good, the second column is looking good, the third column, I've got a negative 1 there. I would really like that to be a positive 1. That's fairly straightforward to do. I'm going to want to take the opposite of row 3. Right? You can take a multiple of any row, and that's still an elementary row operation. So the first row stays the same. The second row stays the same. And we take the opposite of the third row. So 0, 0, positive 1, positive 5, negative 2, negative 1. All right, all that's left is those two entries right there. So it's going to be row 1 minus 9. Row 3, it's going to be row 2 plus 3. Row 3. 1 minus 0 is 1. 0 minus 0 is 0. 9 minus 9 times 1 is 0. 5 minus 9 times 5 is 5 minus 45, which is negative 40. Negative 2 minus 9 times negative 2. 9 times negative 2 is negative 18. Negative 2 minus negative 18 is negative 2 plus 18, which is 16. 0 minus 9 times negative 1 is positive 9. Now we've got 0, 1, 0. 3 times 5 is 15, minus 2 is 13. 3 times negative 2 is -6, plus 1 is -5, and then we've got -3, and then the last row stays the same. 0, 0, 1, 5, -2, -1. All right, and that's the process. The left-hand side of our augmented matrix is now the identity matrix. And as soon as we've achieved that, the right-hand side must be A inverse. So A inverse in this case should be the matrix -40, 16, 9, 13, -5, -3, 5, -2, -1. And here I'm using that fact that the inverse is unique in lieu of proof. I know that there is only one inverse to a given matrix. I have found a matrix that I am claiming is the inverse, and instead of proving that this process always works, I can shortcut that, and if I remember, the original matrix A I can multiply A times my new matrix A inverse, right, using the row and column. First row dot with first column. All right, these are a little bit messy. I'm going to take the time to write them out carefully. I've got 1 times -40, which is -40. I've got 2 times 13, which is 26. I've got 3 times 5, which is 15. First row, second column. I've got 16, -10, and -6. First row, third column. I've got 9, -6, and -3. Second row, first column, I've got -80, I've got 65, and I've got 15. Second row, second column, I've got 32, -25, and -6. Second row, third column, I've got 18, -15, -3. And then the third row, with the first column, with the second column, and with the third column. And doing all of that arithmetic, yes, in fact, I get 1, 0, 0, 0, 1, 0, 0, 0, 1. I can check going the other way as well, but it does give me the identity matrix, and that's what I was after. I mentioned earlier that not every matrix must have an inverse. So in order to demonstrate what I mean by that, let's take a look at one more matrix. Let's call this matrix B. It is 1, 6, 4, 2, 4, -1, -1, 2, 5. And I can set up using the exact same process we used before. Augmented matrix, left-hand side. Is matrix B, right-hand side. Is the identity matrix. And I can start into my elementary row operations. All right, row 2 minus twice row 1. row 3 plus row 1. Two minus 2 is 0. 4 minus 12 is -8. Negative 1 minus 4 is negative 1 minus 8 is -9. 0 minus 2 is -2, then 1 and 0. Then we've got 0, 8, 9. We've got 1, 0, 1. And right here, you can kind of see the problem right away. If you look at the submatrix, that looks like that. But to make it a little bit more clear, let's take one more step, and let's just take row 3 plus row 2. When I do that, the first row stays the same. The second row stays the same. And then in the third row, 0 plus 0 is 0. 8 plus -8 is 0. 9 plus -9 is 0. -2 plus 1 is -1. 1 plus 0 is 1. 0 plus 1 is 1. But the problem is this part right here. Because on the left-hand side, I have a row that is entirely 0. There is no way to come back from that. There is no way to come back from a row that's entirely 0 to get the identity matrix, which has to have a 1 in one of the entries and nowhere else. As soon as that happens, we can say that matrix B does not have an inverse. Or another way of phrasing the same thing, B is not invertible. All right, so that's the process. And I'd like you to take a look at this one. Relatively simple one for now, just a 2 by 2 matrix to get the hang of the notation and what's going on here. But use Gauss-Jordan elimination to find the inverse matrix for matrix C, 2, 2, 2, 0. If the inverse does not exist, explain why. Right. In homework problems, you'll see much larger matrices. I'll have you looking for inverses of 3 by 3, 4 by 4, maybe even a 5 by 5 matrix. We're not going to get any bigger than that because 3 by 3 is generally the nice balance point. 3 by 3 and 4 by 4 matrices show you where things are interesting. Bigger than that, it just becomes a headache that feels like it's a headache for the sake of being a headache. That's about the point where you have to go to a computer and make it do the work for you, which is a little bit beyond the scope of this course. Great. But take a few minutes, see what you can do with the process here, take a look at this particular matrix, and I'll see you in the next video.